Three. Goodness, I need glasses. Okay. All right. Wait a minute.
Okay, can you hear me? Yeah. Okay. First of all, thank you very much for being here. It is a great pleasure. For those who don't know me, my name is Maurizio Pajola. I'm actually a postdoc at the University of Padua working with the Rosetta spacecraft. So great images are coming down right now. I've done my PhD studies between Jet Propulsion Lab for 1.5 years and University of Padua on Mars paleohydrology. But today I'm going to show you one of my best love, which is Phobos. So the title of this topic is whether Phobos' capture origin is a priori excluded from its low bulk density. I would like to acknowledge all the other guys working with me: Monica Lazzarin, Christian Carli, Cristina Dalleore, Ted Rush, Dale Cruikshank, Yvonne Pendleton, Ivano, Albertini, Sarah Magrin, Fiorangela, and Barbieri. So, what is really Phobos? Phobos is one of the two satellites around Mars. It's the closest one. Its mean radius is around 11.1 kilometers and has a bulk density of 1.87 gram over cubic centimeter. It is orbiting around 6,000 kilometers far from the surface of Mars. It is well inside the Roche limit between Phobos and Mars. It has an inclination above the equator of around 1 degree and 26 degrees above the inclination on the ecliptic. The orbital period of Phobos is around 7 hours and 39 minutes. So what about Phobos' surface? This is a Viking map of the entire surface. Phobos is tidally locked. It's showing a face towards Mars, which is called the sub-Mars hemisphere. Then, of course, there is an anti-Mars hemisphere. And on the leading hemisphere, there is the main feature of Phobos, which is a pretty big crater with respect to the dimension of Phobos, which is the Stickney crater. It is a crater of around 9 kilometers. So, in the surface, we can see a couple of units identifying Murci et al. Work in 1996. There is a radar unit, more or less 2/3 of the surface, which is supposed to get older and precise material, while after the impact of Stickney crater is thought to have a blanket on the left side of it, and it's called a blue air unit with fresher material coming from the interior side, of course, of Stickney crater. Just to give you an idea about Phobos, it's quite small, but still it's still important. I mean, I was born in Venice, you can see here, and that's my university, University of Padua. If you can imagine, Venice together with Padua can really be and fit inside just a Stickney crater. So anyway, it's still pretty big, I think. So I have to say that Phobos is not just causing headaches, it is a headache itself. Why? Because there are two main ideas about its origin. From one side, we got the bulk density and the inclination, which are showing that Phobos could be formed from a disk of debris, suggested by Piel in 2007, whether as a remnant of the formation of Mars or as the result of a collision between Mars and a large body. Why should we expect a low density? Because if it is considered like a reaccreted material, then of course there is a large interior porosity. On top of that, there is a couple of observations by Duran et al. In 2011 showing the presence of phyllosilicates consistent with the formation of Phobos near more or less its current orbit. And that's one opinion, one work, I mean. On the other side, there is 43 years of observation, and there is a great summary of work made by Duxbury in 2013, which are showing that the surface spectra coming from below 4 microns, between 0.3 and 4 microns, are showing that the physical characteristics are similar to low albedo asteroids, such as C-type or D-type asteroids. Why Phobos is a headache? Because, of course, it's really difficult to put it in orbit around Mars, you know. So, two major ideas that came out just trying to explain that was binary asteroid dissociation, a work made by Landis in 2009, and then another work made by myself in 2012, having an idea of a collisional capture of D-type asteroids, but still it's quite tough trying to understand how to put that in orbit and being a capture asteroid. Why is an headache? Because a recent paper by Schmedemann et al. In 2013 is suggesting that the surface of Phobos is pretty ancient, between 4.3 and 3.7 giga-years. So this is dating back to a period where, you know, those two different possible scenarios, in situ and capture asteroid, could be supported. So in 2012, I published a paper using the OSIRIS data. I'm working for the Rosetta spacecraft. It's 7 years that I'm working with it. And the Osiris narrow-angle camera is, of course, a camera and has a suite of different bandpass filters. And here, what I'm showing you in the lower side, here, you don't really see, of course, but this is the dispersion of D-type asteroids, and the spectrophotometry of Phobos is well inside that. So it's a hint pointing towards a possible D-type asteroidal origin. Well, in 2013, thanks to guys working here like Dale, Christina, and Ted, we had the possibility to extend the narrow-angle camera bandpass filters with a wide-angle camera covering a wavelength range between 0.25 up to 1 micron. And the model we came up with is a mineralogical model, try to understand the surface, composed of a mixture of Tagish Lake meteorite, but not alone, and the pyroxene glass explaining this surface reflectance. The model is right here, and it's showing 80% Tagish Lake plus 20% pyroxene glass. This is just the Osiris wavelength range from 1 micron up to 0.25, and these are the two models that were competing. But once we extended this fit right here to another, to a bigger wavelength range of Marchi and Erad of 1996 and then the Rivkin 2002 works, we could see that the fit was quite good with respect to from 0.25 up to 4 microns. The second model you don't really see, but it's quite here. So it was not that good. So now, since Tagish Lake is usually used as a common spectral analog for D-type asteroids, this, of course, should provide additional information with respect to the compositional similarities between Phobos and D-type asteroids. But still, what else? Phobos has a mean radius of 11.1 kilometers. So do we expect differentiation of the body? Do we expect layering inside the structure? Do we expect heterogeneity of that stuff? So there is another couple of questions. Does the surface composition of Phobos can help us in understanding its origin? First question. And second, can we assume that the surface composition reflects Phobos' interior mineralogy? So as it was presented in some of the papers, Tagish Lake is a friable carbonaceous chondrite with such a huge quantity of stuff inside, like fine-grained opaque matrix with phyllosilicates, magnetite, siderites, and other stuff. So the idea that I came up with was there is a Tagish Lake density published by Hildebrand et al. In 2006, and this is the value of it. And after that, I was trying to understand what was the pyroxene glass used in Pajola et al. 2013 work, trying to understand what was the density of this crystalline bronzite. And I found out that is around this value, 3.35 grams over cubic centimeter. The only problem is that we don't really have the density of the pyroxene glass. We got the crystalline bronzite, which is the crystalline phase of it. So in order to estimate the density value for this component, we had to come out with different ideas. First of all, we tried to get different pyroxene glasses from the researcher, trying to understand what was their density value of diopside, this here, a mixture of them both, and augite. And then a second idea was using mafic-rich glasses with visible and near-infrared spectra, which are very close to the pyroxene glass here, two gabbronites and one hawaiitic basalt. So using these values, we calculated the glass to crystalline density ratio for the first case, which was around 83 up to 87%, giving these values of density. And in the second case, we came out up to a glass to crystalline density of around 93%, which is that value of density. So after that, we consider a set of mixtures with Tagish Lake fixed and pyroxene glass varying the density value between 83% up to 93% with steps of 2%. And you can pretty understand here that the mixture density right here, if we are assuming that in the interior side of Phobos is composed from the spectral mineralogies that we can see from the surface, it's pretty close to the Phobos one. Okay. So one problem of Phobos is that there are papers telling that there can be a possibility to have a huge quantity of macroporosity, around 40%, if we consider phyllosilicates containing right in the middle, in the interior of Phobos. So I was using the equation 2 of Rosenblatt 2011, And this one is showing what is the macroporosity content that we are expecting once you are considering Phobos bulk density and one rock compound density. This is the plot that we came up with. So these are the different mixtures here. And here you don't really see that this is the macroporosity, but you can see from there were values proposing 40% of the interior side of Phobos should be macroporosity, but here you are just ranging from 3% up to 0%, which are the different 6 mixtures that I was showing you. So it seems like you don't really need a huge quantity of macroporosity if you are using that material that we are seeing from the surface, and if you make that assumption. In addition to this macroporosity for Tagish Lake, this is the formula that I was showing you before, and here, this is the mass fraction of water ice. So the idea is that you can have whatever you like material inside Phobos, just you have to tune the macroporosity and the content of ice right inside it. Using the same material that I was using for the 6 different mixtures, here you don't really see, but there are lines coming from mixture number 6 up to mixture number 1, which don't really need even macroporosity or ice. So the main idea is that the mineralogical model that I was using trying to explain the surface reflectance of Phobos could also bring new insights about the interior composition of Phobos. And this could be really interesting because if you don't really have the possibility to drill inside Phobos or stuff, probably there could be voids and caves inside it. But this could be a possible reconciliation between the surface side of Phobos and the interior composition of it. And with this slide, this is the last one, and that's the 3D model we have printed in Padua right here. Thanks a lot.
I measured some frozen Tagish Lake at Chris Hurd's laboratory, and it adds about another tenth, about 0.15 to the bulk density of Tagish Lake just by having still the frozen water in the thing. So that moves you in that direction. But remember that I was just wondering why the bulk density is a particular, adding in the peroxide glass is actually a constraint on anything. It does work okay for the spectra, but I just don't see that it's a constraint on the bulk density.
Yeah, that's right. The idea is that using from the surface spectrophotometry, what I was doing is, okay, let's try to assume that it's a small body, and in my mind should be an asteroid capture. But is it possible to make like an upside down stuff in order to say, okay, from the surface, that's the spectral reflectance. Let's try to use the same mineralogy, trying to infer stuff from the middle, from the inside Phobos. And we could see that you don't really need that huge quantity of water ice or voids in order to explain if it's possible that was it's not a rubble pile or a captured asteroid. That's the stuff that I was trying to infer. I mean, I have to say that is a simple assumption, but still, I mean, working with the Rosetta spacecraft, I was working on Steins, for example, or other minor bodies. Still, Lutece was pretty big because it's 100 kilometers. But still, it's kind of tough trying to say that there is differentiation inside, such small bodies. That's why I was trying to make this assumption.
One more quick comment. I think it's really in the court of the dynamicists to figure out how we can do this, how we can capture the asteroid.
Yeah.
But I'm just being snide.
Yeah, that's right.
Nancy Chabot, APL. Just a quick question then. I guess, so to answer your title, is Phobos capture origin a priori excluded from its low bulk density? I guess the answer is no. Is that what you're saying?
No, I don't really think, I mean, you cannot a priori say it is a rubble pile, and there is of course also the stuff that is well inside the Roche limit. So if it's a rubble pile, someone should explain me how is it possible not to be a ring, around Mars and not just if it's a rubble pile, you should put inside some glue in order to keep it there, because otherwise it cannot be. Where is it?
Is there time for a question, or are we up?
Not really, but we'll do it anyway.
Okay. I was just going to say on Phobos' density, what surprised me always is that Phobos density is about 1.8 or so, but a lot of our dark primitive asteroids that we have densities for are more like 1.3. Like Matilda's 1.3. Yeah. We now have a small asteroid Bennu. We think that density is about 1.3. And so the question for me is always, why is Phobos so overly dense compared to these other guys? And I'm still confused about that.
No, but that's right. And consider also that Matilda, for example, is 1.3 grams over cubic centimeters of bulk density. So it's an asteroid, and it's not something that was recreated around Mars. That's one thing that I was keeping in mind.
Okay, thank you. We better move